Thank you. Welcome, everybody. Thank you for showing up. I'm Wim van Dam. I'm recently started working at QC Ware, and I've got a long background in quantum computing in academia. And I'm very excited about being here. I'm also very excited about living at this moment because quantum computing has been on people's mind for 10, 20, 30 years, arguably, and we're really getting at this point where it starts to get interesting for a much larger population than just, people in laboratories thinking about the future. It's really getting to be here. And as somebody who has been in this field for quite a while, the progress might seem slow to somebody, but actually it has been much faster than I would say many people anticipated 10, 20 years ago. And it's really an exciting moment that I'm really happy to be able to tell you a little bit more about quantum computing in general. What I try to establish with my brief presentation is establish some common knowledge that in subsequent talks, hopefully it's clear how it all connects together. So I'll be giving a broad overview of things having to do with quantum computing and explain some terms and, more importantly, ways of thinking about how people think and investigate quantum computing. Okay, so I'm going to address three questions. Why do we need quantum computers? Why are quantum computers better than classical computers, potentially? And what are applications of quantum computers? So why would anybody be interested in quantum computers if they don't have an overriding interest in quantum physics, for example? So why we need quantum computers has to do with the potential benefit that they give to solving problems more efficiently. And that's it's a very important notion, this like, what do we mean by efficiently? It doesn't mean just faster. If you want something faster, you just buy a faster computer and you're done with that. What quantum computers try to do and what they're capable of doing is reach kind of an efficiency that outpaces any possible classical computer in some context. And I'll be explaining what I mean by that first. So a problem is, so that occurred to me this morning when I was trying to get here with my own car, how to go from A to B. And you want this to be done kind of efficiently, meaning you won't have the shortest time driving or you won't have the shortest distance driving because your concern is more gasoline rather than time. And clearly this is a problem that is important for everybody, and it's a problem that is not just a single problem. Every starting point and every destination point gives you a new instance of this problem. And the bigger the distance between where you start and where you hopefully end up with, the more complicated the problem is. If your distance goes from 5 miles to 20 miles, there are more decisions that the algorithm has to make. And we say that an algorithm solves this problem for us on our phone or on our laptop if the algorithm can deal with this kind of scaling kind of in a nice, friendly way. Google Maps would be pretty useless if it would only work within a radius of 30 miles, and then if you want to give it a distance of 300 miles, it would say this problem is too big for me to compute. Sorry, I can't help you. Ask me again when you're closer to your destination. We want our algorithm to scale nicely, efficiently, as the problem size gets bigger and bigger. And so, and it works. And we also want our algorithm to be that quickly, that fast, that as situations change as we're driving, that it can adjust. It should not be that this computation takes 5 minutes. Again, that would render the application pretty much useless. And so that's what efficiency is. And scaling as the problem gets bigger and bigger, that we can manage, and hopefully, that it is nimble enough to solve it, pretty much on the fly. Now, this is a practical problem. It's very relevant if you're into delivery. And so what people in the algorithmic field do is they take this real-life problem, map it into a more abstract version of the problem, run the algorithm on that abstract problem, and then pass back the solution to the algorithm. So this is, we know this, we love this, and this is very important that we're able to do this. And it requires fast computers, but more importantly, it requires efficient algorithms to solve these problems for us. So here's another problem that if you're in FedEx or any kind of delivery service, if that's your business, that is also important. Rather than going through A to B, you want to find a route that visits a certain number of distribution points with, again, the minimum amount of time or the minimum amount of distance traveled. So that's a problem that has been well studied as well, and this is what we call in computer science a hard problem, meaning that, so this specific instance, it can be solved, and this is the route that you would have to drive through the US to visit those red points. But you can imagine a situation where there are far more red points, and then what is the optimal route? And this is a hard problem that if you start feeding the algorithm problem instances with more and more red points, the computational time grows exponentially with the number of points that you try to visit. And so we have an algorithm for this problem, how to optimize a route visiting many distribution points, but it's not what we call an efficient algorithm. It scales badly, it scales exponentially with the number of distribution points, which is kind of a problem. We can solve it for small instances, but for larger instances, the computer will just get back to us saying like, the estimate that my estimate, how long it will take me to solve this problem for you is just too long. We'll have to do something different. That's what we call a hard problem. It's a problem for which there is no known efficient algorithm. Okay. So to repeat, the ideal scenario is we've got a real-life problem. We know how to map it into a computational problem on which we can run our algorithm. We have an efficient algorithm, and in real time, it gives us back an optimal solution. And each of these arrows here are important parts of algorithmic design. How to properly take a real-life problem and map it into something that a computer can tackle is a very important problem. The bottom green line, the design of algorithms, it's obviously something that people in algorithmic design work on very hard, and getting back something to the customer that is like useful and that they can act on, that of course is also a crucial ingredient. And so the less than ideal scenario, but truthfully a very common scenario, is that we have a real life problem. We map it to a computational problem, but now there is no efficient algorithm. That if the instance of the problem, if we feed it an input that is too big, that that we don't have an algorithm that does get back to us saying, this is the optimal solution, and it does so in a reasonable amount of time. And this is common, and this is actually intrinsic to certain computational problems. It's not because we're not smart enough. It's because certain problems are just very hard to solve. That's the nature of the beast. But still, we're looking at the situation that we are this delivery van, and we want to visit all those points, and getting back to the person driving the van saying like, well, we don't have a perfect solution. That's not good enough. You have to find a way around this less than ideal scenario. And so, what do we do? What do we do in practice when we're facing an algorithm, a problem for which we don't have a perfect, efficient algorithm? Well, one of them is to design a better algorithm. Try to come up with a better algorithm. Algorithms are designed by people, and so you can try to outsmart the previous designer. Another one that is important and in practice often used is that you say, I don't require perfection. Maybe I should just give up on this goal of finding the shortest, fastest route to visit all those points. Maybe I just want to be within like 10, 20% of the optimal solution. If my algorithm does a better approximation of the algorithm from my competitor, I still have a competitive edge. And so you will be hearing later today about, well, not always the perfect solution. That can be the enemy of good, trying to find a better approximation. If your approximation is better than your competitor, you win. And the third one is get faster hardware. If it doesn't run on this hardware platform, maybe it should run on another hardware platform that is better, more advanced, and that you solve your problem that you could not solve previously. Now, some of you might think that, well, that's bullet 3, and it's about hardware. That's what quantum computing resides. That's, get faster hardware. I'd like to stress that that's not the case. Quantum computing is really quantum algorithms is really the first bullet, that it's the algorithms, the quantum algorithms that give quantum computers the edge over classical computers. And so the algorithmic design for quantum computation is a very important part. We want to build the machines, obviously, but we also should find the new algorithms that work on this new hardware. We have to do both things. Both the hardware and the software development has to happen hand in hand, step by step, to reach this goal of quantum computers doing a better job than classical computers. And so it would be appropriate for me to say a little bit like why can these quantum computers do this? Why do we think that, you know, for certain problems a quantum computer is the way to go? Okay, so you're going to learn one word if you haven't learned it already. That is qubit, and qubit is just a shorthand for quantum bit. And obviously it's the most basic element of a computational device. And right there I would say lies the big difference between classical computing and quantum computing. This is not going to turn into a grad course on quantum algorithms, but let me just give you the highlights. That classically, a single bit, of course, is either 0 or 1. And so your bit is either in that top position or the bottom position. Now, a quantum bit can also be 0 and 1, but it can also be many things in between. And the way to kind of think about this is that you've got this sphere where the North Pole is the 0 and the South Pole is the 1, but at any point on the surface, or actually also the inside of this sphere, is fair game for a quantum computer. And so when you think of a bit, you know, you can apply a NOT gate. The simplest non-trivial thing that you can do to a bit is flip it. With a quantum bit, you've got this sphere, and so you can do much more things. You can rotate this sphere. And so when you listen to talks about, you know, implementing simple quantum computers, you will hear people talk about rotation gates. What are they rotating? They're rotating that sphere of a single qubit. Okay, so that's one qubit, and of course, you know, one qubit is very interesting, but it really, things really start to pick up when you've got like many qubits, and then, you know, the corresponding shape becomes like bigger and bigger and bigger. As you get more and more quantum bits, it actually grows exponentially in the number of quantum bits. And so clearly this sphere has like many more possibilities. And if I imagine a near future device which has like 100 quantum bits, it is a sphere that lives in a dimension 2 to the 100, which is, well, it's humongous, that if I want to describe a single system that has 100 quantum bits, and I want to describe that faithfully on using just a classical hard disk, I would need 140 terabytes. It can be done, this is important, classical computers can simulate quantum computers, but it comes at a tremendous cost. And that has to do with how the nature of quantum information is different from the discrete nature of classical information. So right there, the data that you have is a whole different kind of beast. There are many more possibilities if you have 100 quantum bits compared to 100 classical bits. But data is not enough. You also want to kind of figure out, like, what can I now do with this data? And so when you go to that sphere and you're kind of on the equator, you're in a situation where the system is both 0 and 1 in a certain way. And if you run now a computation on this system that is both 0 and 1, you're running it both on the input value 0 and the input value 1. And so what a quantum computer and a quantum algorithm does is it creates this, what's called a superposition of these possibilities, runs the algorithm once, and effectively does a computation in parallel, and then in the end of the day, these different computational outcomes get combined using interference, which you can see with light and water, to get the desired outcome. If you think of a computer like performing a computation that is like walking a path from the input to the output, classically it would be a deterministic path like you see in the top figure, where, you know, it's left, right, 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 left. Whereas a quantum device, on starting at a specific input, it will like spread out its walk. It will start to kind of wander all these different paths, these computational paths at the same time. And the design of the algorithm is such that at the bottom, the overwhelming outcome is the one that gives the correct answer. And so you will hear people talk about like superposition, interference. That's what this is, that you run your algorithm in superposition, and that interference will take care of giving the speed up in the end over classical computing. Okay. So is there a historical precedent for it? And I had to think long and hard, and I found one kind of 1,000 years ago, is that you have the very natural problem of like doing mathematics, division, multiplication, using some kind of numerical system. And I realized that this person, Pope Sylvester II, should really be the saint of quantum computing, except for he wasn't a saint, he was only a pope for 3 years and never made it. But he was the person who kind of introduced or reintroduced to Europe the place value notation that we use nowadays to do arithmetic. And implementing this notation using an abacus. And by doing so, he could perform speedy calculations that were extremely difficult for people in his day to think through using only Roman numerals. Sorry. So think of like a big computation, and you want to do it with Roman numerals. That's like classical computing. Now think of like that same computation that you want to perform using the decimal system that we use, which can be implemented much faster. That's quantum computing. It's a new technology that solves a known problem in a way that is fundamentally more efficient than the old ways of doing. So what are some of the applications of quantum computing? What does all this dreaming about, like, can we use quantum mechanics to solve our problems, what does that get us? Let me go through 4 examples, which will be discussed in more detail in subsequent talks. The first one is searching and optimization. And I consider this a problem that is so tailor-made for the current hardware that we have that I think that this is like of the applications that we're going to see happening, that this one will be the first one. That this one really, we're at the cusp of doing some really interesting results that are going to be important for a large community. And so the idea is that you're solving an optimization problem. And for anybody who has like thought about optimization problems, you know that you have a good solution, but there might be a better solution out there. And there is this problem like, well, how do I go from my good solution that was easy to find to my better solution that is harder to find? This is like walking in a landscape, and you try to find the lowest point, and you're in a local valley, and you need to kind of traverse over, some solutions that are worse to get to the global minimum. Now, quantum computers use quantum physics, and quantum physics is famous for being able to tunnel through barriers. And with this idea, we've developed several algorithms that have great promise for solving your optimization problems more quickly, more efficiently than is possible using quantum computers. And so that I find is my #1 application, I would say. Now, also very natural to consider, and historically the first one that people thought about is that people in material sciences, people doing biochemistry or chemistry, anything that involves simulating quantum physical systems, you run into this wall that it is very hard on a traditional computer to simulate the quantum physics that is going on. Now, obviously, if you have a quantum mechanical device, the quantum computer will have no problem simulating quantum physics. And so quantum computers will be exquisite in simulating quantum physics. It's almost, they're literally made for that. And so in material science, in biochemistry, the prospect of having a device that simulates we imagine a new material and we wonder what are the properties. And well, the solution that we have nowadays is that you will have to build it, you have to run experiments on it. But if you can just model it and efficiently run your simulations and figure out all these properties that you're interested in, there is a tremendous gain in speed. You will be able to do it much faster than building the experiment. It will be cheaper. You will be more flexible. All these things will have great promise. And I consider this medium term because I think the devices needed for this are going to be a little bit bigger. The required size to implement these things is going to be a little bit bigger than the previous example. But it is one that quantum computers are like, I mean, that's what they're built for, doing quantum physics for us, so we don't have to do it. Famously, I would say an application is Shor's factoring algorithm. This is the algorithm that started the field in 1994 when Peter Shor, then at AT&T, discovered that a quantum computer would be able to break cryptography. Namely, you take a large integer and you find its prime factors. That might seem like an esoteric problem in mathematics, but it's at the core problem, that this is a hard problem, is why we consider HTTPS, the S stands for secure, to be a safe public key protocol. And so we know that if we have a fully fledged and large quantum computer, pretty much all the secure communication that we're doing nowadays will be broken. So this clearly is an interesting problem, but it really requires a fully fledged quantum computer. So in the end, I consider this a long-term application. We're going to do the first two things first before we have a device that is powerful enough to do this. But of course, you have to realize that, well, some secrets you want to keep not for now, you want to keep them for a long time. You want to keep them for 30, 40 years. And you're communicating encrypted data publicly. So clearly, anybody can store your public communication and wait for another 20 years for that quantum computer to show up, and retroactively can read your messages of 2 years. And you have to ask yourself, well, the secrets that I have, am I comfortable people knowing it 20 years from now? Maybe you are comfortable with it, but maybe you're not comfortable with it. So there's a retroactive aspect to this business of breaking cryptography that is relevant now. And a fourth application is machine learning. Machine learning deals with large amounts of data and uses a lot of linear algebra. Now, quantum physics is all about large amounts of data and linear algebra. This is I'm loath to put a prediction on how quickly or how late we will see applications of this, but really, when you think about it, quantum physics and the aspects of machine learning that make it, a computationally demanding tasks, they combine nicely. And this is a very exciting, more recent development that people have started to look at, like, well, all these things that we're doing on those supercomputers nowadays, what would a quantum device do? And there's some promising results there that, yes, there will be a quantum benefit in this situation as well. And with that, I'll thank you, and I'll be happy to take your questions. Yes, let's wait for the microphone. There's somebody running. Could you stand up? Then you can see where it is.
Regarding applications in machine learning, how do we expect quantum annealing machines to help minimize cost functions in machine learning applications?
How do we expect quantum machine learning? So quite often in machine learning, where we're dealing with a large amount of data, and we try to find, in this data, like, what are the important components? What are the principal components in this data, and how are we going to find this out? This boils down to quite often a problem in linear algebra, that you've got this large system of linear equations and you want to find a solution to it. But that these systems are exponentially large, and that by encoding these linear system in a superposition, you can compress it in a much smaller quantum register. And if you're only interested in certain aspects of your data, the most principal components or something like that, then you can distill that from this much smaller system. So it's really taking that exponentially large problem and mapping it into a much smaller quantum system that still then contains the important features of your data. Yes. There's another question over there. Thanks.
Hi, I just had a quick question regarding the inference step that you mentioned in your quantum computing algorithm. So I was just curious, like, what were some of the examples of like general heuristic algorithms that you wanted to use? Like, for instance, were you guys looking, at potentially like quantum phase estimation, or are we like looking at performing or constructing like the parent Hamiltonians for the many body states? Like, what is that inference step?
Sorry, I could not hear that properly. Could you?
Sorry. So you were mentioning that when we are running, like in one of the examples that you provided, there was a case where you said, okay, so after we come up with these solutions in the superposition, we then run a subsequent inference step, right? Mm-hmm. And so I was just curious, like with respect to the inference step, are you guys looking at situations such as, maybe constructing like parent Hamiltonians from many body states? I wasn't sure because there's so many alternative ways to do the inference step.
Right. So I got to say that the inference step is not like something you do at the end. It's something that you kind of do throughout. So the deal with the inference is that it's not enough just to run many algorithms in parallel. I mean, that's classical probabilistic. That's like random sampling, and we already do that all the time. So what you want to do is that this quantum sampling is that you, throughout the process, make sure that the phases, the amplitudes, are such that throughout the process, the bad cases kind of cancel each other and the good cases kind of survive. So there's no single answer to how do you do the inference. There's like no magic step where you say like, okay, and now we're doing the inference to get what we want. You have to design the algorithm throughout to make it work. And for each problem, that is like a new problem to kind of resolve how you're going to make these cancellations work out. Yeah. Oh, there's a question over there.
Thank you very much. So when you had these 4 applications identified, you specified by saying near term or short term, long term, and then formation. So now what does that ride on? So does that mean for something like, if you look at NISC, the chances are the short term ones can be solved in near term, or I'm trying to understand what was that, how did the timing factor show in, and then what is that machine learning when you said we don't know, what does that mean?
Right, so what makes me say long-term, short-term for various algorithms? What we're doing with the various algorithms is that we kind of try to map it into, okay, this is the problem, these are problem instances I'm interested in. Now, if I map that to a abstract problem that I'm going to solve on my quantum computer, how many bits are required? And so it's really, one big indicator is how many quantum bits do I need to solve a problem that I care about. And for certain problems, it's the mapping can be quite inefficient. What seems like a small problem, if you write it out, it becomes much bigger, and then it becomes more like midterm rather than short term. So that's one aspect. How many bits do we need to write down the problem? A second consideration is, what do we want to do with those quantum bits? Clearly, these quantum mechanical devices, they're in a lab, and they will typically be in a two-dimensional array of quantum bits. Is it sufficient that the bits can talk next to each other? That's good. But if we want all the quantum bits to talk like cross with each other, that poses another experimental challenge. Now, a third aspect that makes us say, well, midterm, long-term, is that how good are the existing classical algorithms? And that's the problem, for example, with factoring, that we have actually really good algorithms for factoring, for breaking code, because people have been thinking about it for like 2,000 years. And so what is the competition? How good is the classical competition to my quantum algorithm? So these 3 aspects kind of all play a role, and that kind of made me say, short, medium, long term. I hope that kind of addresses your question. Yes. Okay. Well, I'm spot on time. Thank you again.